Hey guys, this is W3C Ray, and today we will look into the mystery bounty math and my personal take on how you should calculate the bounty value in the mystery bounty format. So let's hop right into that. Mystery bounties are like the SKO format, meaning you have a portion which you put in a regular prize pool and you have a portion of the buy-in which you put into the KO prize pool. But very different to the normal SKO. The bounties which you can win are random. So you have like a minimum bounty value, and then the bounty value can go up to like 10% of the prize pool, 20% of the total KO prize pool. So the max bounty which you can win in this format is way higher than in an SKO, where the value is very defined to if you play 100 plus 100 SKO, then you can win $100 if you bust a player. Meanwhile, in the mystery bounty, if you play 100 SKO mystery bounty, then, well, if the field is very big, then you can win a million bounty or whatever. The bounty value distribution, so how many big and small bounties exist and how big the biggest bounty is compared to the smallest bounty, can be quite skewed, meaning that like you can be very top heavy in those distributions. There can be a lot of the KO prize pool in like one bounty, and depending on the field size, if you have like a big field and you have very few players who hold a lot of the KO prize pool because like they are distributed randomly, this big bounty makes this format like on the one hand probably quite interesting, quite gambly, and on the other hand it's like not so great in my opinion. It's not so great in my opinion because, well, if you cannot like really calculate ahead that you will be often enough able to bust players with high bounties, then recreationals will take a lot of the KO prize pool just by chance because the biggest bounties are not sitting at your table or not sitting at a table of a rec, but recreationals will take the biggest bounties out of the KO prize pool, and then a lot of the prize money, which you also partly paid for with your tournament buy-in, is already gone. So, in my personal opinion, yeah, maybe it's fun to play those tournaments, but it's not like the best format to make money. I will regard here that the bounty phase usually begins in the money for those mystery bounty tournaments, meaning that you're not like from the start of the tournament, if you bust a player, win a bounty, but let's say in phase 2, so you play a lot of phase 1s, and then there's a phase 2 for this mystery bounty tournament, and there then you can win bounties. Or for a live tournament, not at day 1 you win bounties, but at day 2 they start distributing the bounties. So keep that in mind. Most of the mystery bounty tournaments have this format that you are not winning bounties from the start, but only like after a certain amount of players busted or after you made it through a certain phase or yeah, certain days in a live tournament. Let's hop into the calculation. So the calculation is actually quite simple. If you like look at it simply, it is a SKO calculation. So I give you here example from a live tournament. This was a 3,000 euro mystery bounty tournament in Barcelona, I think. And again, we have our two prize pools. We have in this specific tournament here 1,700 euros from each player, which goes into the regular prize pool, and we have 1,000 euros from each player, which go into the bounty prize pool. And the calculation now is quite simple. So we divide the 1,000 euros, which are coming into the KO prize pool, and we divide it by the total amount of money we have to pay for the tournament, disregarding rake. So essentially, the money which is actually being played out and not the money which is played out plus the rake. And then we end up with 37.03%, so 37% of a value of a bounty in chips at the very start of that tournament. Now, this tournament had also the feature that it would distribute the bounties not at the start of the tournament, but after day 1. So at day 2, they started paying out the bounties. And at day 2, 450 players of the 1,109 players which started the tournament were remaining. Now, what is the value now of the bounty in day 2? And the average value of the bounty is quite simply the bounty prize pool divided by the remaining players. Since all of the bounty prize pool is left, but some players did already bust, like the average value of the bounty is not 1,000 euros anymore, but higher. So how big is the average bounty? Well, it's the total KO prize pool, so the 1.1 million approximately, since we had 1,100 players. 450 players are remaining, so the average bounty value on each player now is 2,464 euros. And now we can easily calculate this bounty value recalculated in chips, since we know, okay, now it's 2.46 times higher compared to the start, so this value is 2.46 higher than the 1,000, right? We have 2,400 euros and we started with 1,000, so we have a multiplier, and this multiplier we easily use on our calculated start value, so the 37% of a starting stack at the very start of the tournament. Now some players did bust, the average value of the bounty goes up, and we just multiply our multiplier here with the start value of the bounty in chips, and we end up with approximately 91% of a starting stack. So if this tournament had a starting stack of 100,000, then now you would add 91,000 to the pot each time you can bust a player. We can prove this by EV calculation that this 91% of a starting stack value is true. First, we would start with example here again. So we had a spot that 80k stack open jams from the small blind, and for the sake of simplicity, small blind open jams or folds. So he has not like a very well constructed all-in limp open raise strategy. We just want to show that the calculation is correct. We are at big blind 5k, so the small blind has 16 big blinds here effective. And this is the table from the information from a tournament. So we had a 3,000 euro buy-in, 1,700 euros in the regular prize pool, 1,000 in the bounty prize pool, players which started the tournament, players which are left at a certain point. This is the total bounty prize pool and the average value of the bounty, and we already calculated the 91% bounty value percent in starting stacks. The starting stack in this tournament was 30,000 chips. So the average stack when 450 players are remaining is now approximately 74,000 chips. So the small blind has approximately average stack. From this calculation, I already showed you in a video how to EV calculate the value of your stack. You would calculate the EV if you win the hand, you would calculate the EV if you tie the hand, you would calculate the EV if you lose the hand, and you would compare like all of those three outcomes if you call them in to the EV of folding pre-flop, so in this case losing your big blind in the ante. And I calculated that in HRC and got a certain dollar amount for a certain combo. Here I checked it against pocket deuces, if we would call pocket deuces, and what small blind would open jam in Nash Equilibrium if you can only open jam, and those two EV numbers matched. And with a simplified formula, you can calculate the needed equity then, and this was 39.1%. So we needed approximately 39.1% minimum equity against our opponent's open jamming range. And this calculated equity here, we will now check again with our calculated start stack value. First of all, I'll show you that the solution is completely true. Here on the left, you can see the setup which I used in HRC. Then you get a certain outcome in calling range against the open jamming range from the small blind. Here was the EV of the deuces, which I checked, so the $1,400. And if you take the 39.1% minimum equity and put it against the small blind open jamming range, then this will be the result. So the result in Equilab matches the result in HRC, meaning that first of all, our EV calculation is correct, and second of all, our calculated equity here at 39.1% minimum equity is also correct. So 39% equity should be what we are getting if we add 91% of a starting stack to the pot and get our pot odds, then get the equity. This is like the last step now in this whole calculation routine, which we check against so that we make sure that all of our calculations are correct. And this is what we do. So our odds are calculated by, okay, the small blind open jam, so his stack is in the middle. Then we will add to the pot all the entries of the other players and ours, just for the sake of simple calculation. We have our big blind in the middle, and we have this additional bounty value, so the 91% of a starting stack, and we would divide this by the open jamming value, so 80,000 chips minus the big blind, right? So this is how we would calculate our odds. If we put in the numbers, so 80k was the chip stack value of the small blind, then we have 6 times the antes, we have the big blind, then we have the 91.2%, which we calculated the value of bounty, of the average bounty, right, in chips. So this would be here the bounty value, and we would divide this by, again, the small blind stack minus the big blind. So I think I had a 7-handed setup here. 1, 2, 3, 4, 5. Yeah, it's a 7-handed setup. This is why we have 6 times the ante here, and I disregard the ante of the small blind since he's like jamming his 80k. So this is our odds then, 1.558, and equity is 1 divided by 1 plus pot odds, so our needed equity is 39.08%, which within like rounding errors matches the value which we calculated before here, the 39.1%, pretty well. So all done, it's a match. The calculation of getting the starting value of the SKO case in the mystery bounty, and then if you're only paid at a certain point in the tournament when some players are already busted, then multiplying this starting value which you already calculated by the average bounty multiplier. So if it's now like if half of the field is busted, then you have 2 times the value of a starting bounty, so you would multiply your number, the 37%, which we calculated at the very start of the tournament here, you multiply it by 2. Now in our case, well, there was like a little bit more people, then like you halve the field, you more than half the field here, so you have a little bit of a higher multiplier, then you will end up with 2.46 times the starting value, so 91%. And like all calculation, in the end is checking out, you get the correct equity, and yeah, we are done with this simple mathematics on the mystery bounties. So now you probably ask, okay, what took you so long to push out this video, since the math is actually quite simple. And yes, the math is quite simple on this mystery bounty format, but like from the start, I had like a lot of issues with just taking raw EV in this kind of format. So I give you like the extreme example. Let's assume we play a tournament, 1,000 plus 1,000 euros, no rake, and like let's put the extreme case that one player is getting the full bounty prize pool on his head, and the rest has no bounties. So one player has one bounty of like 1 million, and the rest has 0 bounties in this tournament. And the calculation would still be the same. The average value of the bounty, if you would bust a player, is 1,000 euros. Since 1,000 players are remaining, the total prize pool is 1 million euros. And then you would divide it by 1,000, and yet the average value is 1,000. Then you could calculate again the value of a starting stack. Here it would be 50% of a starting stack, and you would add that to the pot. But what is the point of that? The probability that the player with the $1 million bounty is sitting on your table in a 1,000-player field is already like very, very, very slim. And then that you get the situation against this certain player to bust him for the bounty, the probability is also very slim. So this like average value means that you're like a lot of the times adding chips to the pot, then calling off a way wider range against an opponent who has like very likely a bounty of value 0 on his head, right? So if you would have known that, you would have not added any chips to the pot and you would have just played this tournament as a vanilla. You see, like, there is the problem. The more skewed the distribution for the bounties in like the extreme direction is that you have a lot of the bounty prize pool on very few players, the more I dislike the idea that you go there and use the average value of a bounty as your basement calculation on how you would change the needed equity to call off all ins. And I now try to give a better way, or like a more, in my head, more meaningful way to deal with this mystery bounty format. And yeah, let me put a clear yes here. Yes, it reflects the long-term EV. So if you play this tournament like very, very, very often, you will eventually win the 1 million euro bounty at some point, and you will cash in all of the EV of all the times before we didn't win the $1 million bounty. But like, this variance is like insane. So what is the probability that you get in the spot that you're busting this one exact player who has the 1 million euro bounty on his head? The variance, you can imagine, right? It's so high that you would not even start playing this tournament. You could essentially go there, play a vanilla 1K tournament, and then pay 1,000 euros in a lottery and either you get a ticket where the $1 million is written on, or you don't get the ticket. So in this like very extreme case, this is a quite stupid format, as you can see. And of course, this is not how online or live the mystery bounty tournaments are working. Usually the prize pool is obviously spread amongst all players. Everyone has like at least like some dollars on his head to make people play for the bounty. But the more and more skewed like this distribution of how the bounties on the players are distributed is, the more like gambly and stupid becomes this format. So my point is here, the more it's tilted towards some players have a lot of the bounty values on their heads, the less you should take the average value calculation, and the more you should go into a different calculation of how you should deal with this bounty value. And if you sit there and say, okay, I can take the variance of like flipping against 999 other players for one bounty, so essentially for one lottery ticket, if you say, okay, that's all right, I have good high enough bankroll to play those kind of tournaments and I care for the EV, then yeah, okay, go for it. Always add your 50% of a starting stack in this particular extreme craze and put them to the pot and then play for the bounty, right? So the point is here, is it really clever to use an average calculation on an experiment or an event where like the positive outcome is very unlikely and negative outcome or zero outcome in this case, so a lot of players don't have a bounty and only one player has a bounty, is this really clever to use an average calculation? And this actually falls like more or less in the extremes of the so-called St. Petersburg paradox. I highly recommend to check this out if you're interested in mathematical paradox. So the St. Petersburg game is a game where you can actually win infinite money and the expected value of the game is also infinite, but you would not pay a lot of money to play this game, although the upside is very high. And in this game, you essentially flip a coin over and over again, and you win money dependent on how often, let's say, heads come in a row. Okay, and if you have like 15 times heads in a row or 20 times heads in a row, then you get a lot of money for that. But the probability that 20 times heads in a row comes if you flip a coin is very, very, very small. And you would actually not gain a lot of money from this game. And dependent on how you arrange like the bet versus the payout, you can actually lose quite a lot in this game, although the EV is infinite. And yeah, that's also here my point, if you have a game where you have a very big upside in a very low probability, then you would actually start decreasing your own bet, or in our bounty case, the chips which you would add to the pot. So over the next couple of slides, I will give you an idea on how I personally approach those mystery bounty tournaments, how I would calculate, uh, let's say, meaningful number for the chips we would add to the pot and then get our equity from there. I would not use here the arithmetic way to calculate the average, but I would do it a little bit different. And I will give you two examples from the real world now, where also the calculation of the average just by arithmetics is not very meaningful. And the first one would be that you could compare this problem to the question of if you go out on the street and you would ask the people, okay, what is the average wage which you get in a year? Then they would give you a number. And especially in very like economic driven societies, this can spread quite far. So we have like people who earn a lot and we have a lot of people who are not earning that much money. An average value is only meaningful or only reflects what happens in reality if you can check it against reality. To make it like not so abstract, here in this average wage question, I would first, based on data, calculate an average wage. Let's say it's $50,000 a year. Then I would go out on the streets, ask 20 people, and I would expect out of those 20 people, like 15 should be in the range between 40,000 and 60,000 a year. But if I go out with my calculated value of $50,000 a year average wage and I ask the 20 people what is their wage and 15 of them tell me, well, it's 30,000 or less, then I must say my calculated value has nothing to do with reality. So this average value which I calculated beforehand is actually complete meaningless for reflecting reality when I actually ask the majority of the people what is their average wage. And on the next slide, I show you now an example from the real world. Here we have the income distribution in the USA of 2011. And what you can see here on the y-axis is the percentage of total income in the US. And here you have 5 groups of people, so 100% of the population. And you have the lowest 20% of the population here in terms of income and the highest percent of the population here in terms of income. And what you can see is that over 50% of the whole income in the US is distributed to only top 20% of the people. Now, in my experiment where I would now calculate out of those numbers the average wage of family or a household in the US, would be actually for 2011 approximately $70,000. So if I calculate this value and now go out on the streets, I would expect that if I ask 20 people, that at least like 15 of those 20 people would tell me, yeah, I earn in between like $60,000 to $80,000 a year. But that's obviously not the case. So the red line here is the calculated mean, and the blue or black line here is the actually calculated median. So median is a different way to calculate an average value on a distribution. And if the distribution is looking like some earn like very few, some earn a lot, but the majority is earning like the same value, then mean and median are netting the same number. But if the distribution is very skewed in one direction, either a lot of people are earning not so much money or a lot of people are earning a lot of money, then the median will go in the direction of the extreme. So in reality, the calculated average wage here is approximately, I don't know what this is, $45,000 in median. So if I now go out on the streets and ask the people, okay, what is your average wage? Actually, the truth is the people would say, yeah, well, I earn in between like 35 to $45,000 a year, and not in between 60 and $80,000 a year, what the mean suggests. So in this specific case, the median calculation would give me like a way more meaningful number which I can check against reality. So conclusion, in some distributions the mean calculation is pretty meaningless, and in poker if the mean relates to the EV, then the EV might be meaningless. So if we base our bounty calculation, which we then get chips, we add those to the pot, get a new equity, and then call off all-ins based on this equity which we calculated. If the starting point calculating the mean is not reflecting like the quote-unquote most likely EV which we are netting, then this is not a good way to calculate actually what our expected value is. I give you another example, and I want to discuss a little bit more the difference between a mean and a median. So the mean is just the arithmetic average. You have two numbers, you have the total bounty prize pool, and you have the number of players remaining. In our example at the very start of this presentation, it was like 1.1 million euros in total chaos in prize pool, and you had 450 people left, and then you get just the arithmetic average, which was 2,400 euros. And using the mean, let's go to the bottom here of this graphics, can, as I already showed you in the slide before, lead to a value which is actually not reflecting reality. And here you have the height of people, and here I did draw a distribution. So this distribution would actually be like quite linear in terms of how we would reflect the height of the people in the population. So I would calculate out of this distribution here a mean, and then if this would be, for example, 1 meter and 70 centimeters, I would go in this country out on the streets, and if I'm 1 meter and 70 centimeters tall, I would expect that most of the people are like in between my range, so I would not be way taller or way smaller than them. But if we had like population where we have like very tall people, let's say we had people which are 3 meters tall, but most of the population is actually small, and I get here an average height of, let's say, 1 meter and 85 centimeters, I would again expect to go out on the streets. If I'm 1 meter and 85 centimeters tall, I would expect that the people on the street are actually my height, like a little bit smaller, a little bit taller, but in between, let's say like 1 meter and 80 centimeters and 1 meter and 90 centimeters. But now go on the streets and still everyone, or close to everyone, is 1 meter and 70 centimeters. So most of the people are actually way smaller than me. So I check again my mean value against reality, and I just see, okay, this mean value is actually meaningless because most of the people are smaller than I am. And you would deal with this problem with so-called robust statistics, where you would use the median. So cut your distribution here exactly in the middle. And if you do that, then you disregard outliers, either on the like very extreme case that people are way taller, or you could also do this like in the other direction, where people would be like, some people would be like very small. You would always net the same median. So let's say here the 1 meter and 70 centimeters, and then I will check this against reality, and I see, okay, yeah, most people are actually in that height range. So a better way of calculating the value of a bounty in mystery bounties would actually be to calculate the median. Now is the problem, you cannot calculate the median fast because you need to know the exact distribution and then put a like graphical average. So you would cut this distribution exactly in the middle. And this is of course a task that like no one can do fast, and also like close to no one can do anyways mathematically. So although we now know a nice way to calculate actually a good value for the bounty, we cannot do it. That's disappointing. But now I'll show you a way like how you can like get very easy, very close to this value. And we would use the so-called truncated mean. And like, don't be confused with this wording. I will explain it later on, and it's way easier than you think. I just want to use like the correct term. And what does it do? Well, if a lot of the bounty prize pool is on the head of very few players, then we would just disregard this part of the prize pool and we would calculate the mean without this part of the players. And I will give you an example here. So this is from the WSOP online. This was a $100 plus $100 mystery bounty. And here the start bounty value is 50% of a starting stack, since the buy-in in this tournament is exactly equal. $100 in the regular prize pool and $100 into the bounty prize pool. And it was a phase tournament, so there were a lot of phase ones, and in phase two, the distribution of the bounty begins. So if you bust a player in phase two, then you would get bounties. If you bust a player in phase one, then you won't get any bounty. And 5,800 players did enter the phase two. We had a total KO prize pool of $5.1 million. And now look into like the top bounties which were distributed in this tournament. There was one bounty which was $1 million, and then one bounty which was 460,000, two bounties which were 180,000, and four bounties which were 93,000. So if you add those 8 players together, the value of the bounties which they had on their head, then this would net to a total of $2.2 million. So $2.2 million are on the head of 8 players of this 5,800 player field. Now, yeah, you can like imagine how improbable it is that you sit with one of those 8 players at the table and get a chance to bust them. It's actually very, very slim chance that you have those. And I would suggest that you use a truncated mean calculation. Let's start with the mean calculation which we did before. So we have this $5.1 million in the KO prize pool. We have 5,800 players left. So we get an average value of a bounty of $880. For those $880 of average bounty value, we would actually add 2.2 complete starting stacks to the pot every time we can bust a player. Now, I would not do it that way, but I would calculate the truncated mean. And this means I take the $2 million just out of this KO prize pool. I say, okay, it's very improbable that I like even have a chance to win those bounties. And if by chance I have this guy on my table who has this specific bounty and I'm like lucky enough to bust this player, then yeah, all good. Like I won the lottery. Okay. But on average, this will not happen. This would be a very unlikely outcome of I'm calling an all-in and win the bounty. So I will just disregard here the 8 players, the bounty of the 8 players in my total calculation, and just subtract $2 million from the $5.1 million prize pool. So I would calculate here my truncated mean, and this would be $3.1 million divided by 5,800 players who are still in the phase 2, and I will get a value of $535. So every time I can bust a player, I would add 1.35 starting stacks to the pot. So I will actually need a little bit more equity to call off all-ins. But I'm like more in the safe zone, not chasing for like those very improbable situations that I actually have the player with the high bounty on my table, but I will just respect that I will win a bounty because people will have bounties on their head, but most of the times people will have the min bounty on their head or $1,000 bounty in their head, but not the 93k or 180k or the million, right? So I would just take out a little bit of the price pool and then calculate my average from there. This is how I do it. Again, you don't have to do it that way. If you think that you just want to do a raw EV calculation, regard the full bounty price pool, and then, yeah, increase your calling range even more because you did add more chips to the pot, go ahead and do it. It is, in the end, the correct mathematical description for the EV you have in this tournament. But I personally dislike this, like, let's say, plain calculation of EV because expected value must be like a meaningful number. And I would say the way we calculate it here is way less meaningful for the true EV we will net on average in this tournament compared to the calculation I suggest. And that's it from me on the mystery bounty calculation. I wish you a good day and see you soon. Bye bye.